Welcome back. Today we're going to be talking about operations involving polynomials. Specifically, we're going to ask and answer how we can cube a binomial. The first set of examples are intended to be an exploration. So what I'm going to do is I'm going to do two examples with you, and then I want to pause the video. I'd like you to pause the video, see if you can pick up the pattern, and try the second two examples on your own. You'll notice a very similar pattern between the two of them, so it should not be too difficult to pick up. All right, the first thing that you want to do is you want to rewrite it as a product of the first and second powers. So notice that has been done for you. If you notice the second one as a factoring shortcut, you are correct. It is a perfect square trinomial. So we're going to rewrite the second one as what it is, a perfect square trinomial. We're going to follow that by multiplying together, using the distributive property to multiply them out. So I get x times x squared, x to the third, x times 2x, 2x squared. You can follow the pattern throughout as I distribute one number to the next. The final step is to combine like terms or write in standard form the final simplified expression. You'll begin to see a pattern emerge as you do this, and that is intentional, so please pick up on it and notice how it's going to work. So now we're going to involve two variables so we can get a general form of this particular set of properties or set of processes. So again, we recognize that second one as a perfect square trinomial. Rewrite it as a perfect square trinomial. Using the distributive property, we distribute through. However, you have to be very careful because it does get a little bit complicated with your variables. So pay very special attention to make sure that you are putting the square on the proper variable and leaving the other one the first degree. We're going to follow that up by rewriting in standard form or combining like terms, and you can see the pattern begin to emerge. The coefficients of each of your terms is the same, 1, 3, 3, 1. That pattern is going to be useful for you, especially when we get towards the end of this note session. You'll be able to do a little bit of work on that using just the pattern rather than trying to distribute it all the way out. I'd like you to pause the video now, and I'd like you to practice your distributing skills and try to determine what the simplified standard form of these two expressions will be. All right, after pausing the video and working through these, your solution would be recognizing a perfect square trinomial, using distribution to simplify the terms, combining like terms to write it in standard form. Likewise, with two variables, we get the same process, perfect square trinomial, distribution of all terms, combining like terms to simplified standard form. Next, we're going to talk a little bit about something called Pascal's triangle. I want you to take a look at the pattern that you see in the triangle to the right. You'll notice that our coefficients show up near the bottom of this particular triangle. We've gone ahead and simplified a cube or a cubic binomial, so we can relate that to what we see in Pascal's triangle. The third row indicates that we are doing a cube or a triple. We're going to describe a pattern here of the exponents in terms of expanding our binomials. And then part C, we're going to explain how we can use the patterns in A and B to find the product of this particular binomial cubed. So the first thing we're going to identify is that the exponent is 3. The first term is the product is going to be the first term of the binomial cubed times the second term. I'm going to continue on through. Okay? So essentially, what's happening here, oh, that's supposed to be an exponent. Apologize for that. It didn't copy properly, but that's okay. Essentially, what we're saying here is that we're going to be counting up and down simultaneously using the 0 power to, in this case, the 3rd power. So that means that when we look at this particular term, 8x to the 3rd power, that's going to be this term cubed and this term to the 0 power. When we look at 36x squared, what we're looking at here is this term squared and this term squared, but notice that it's got a coefficient of 3. When we're looking at this term, what we're looking at is this term and this term squared. And then, again, a coefficient of 3. And then we're looking at this term to the 3rd power, and then that other term to the 0 power. We'll be looking at this in more detail in just a few minutes, so if you're confused, just kind of roll with it, and we'll work through it together. The way you can find the cube of a binomial at this point is to do what we did in our first set of examples, and that's going to be to rewrite it as a single degree and a degree of 2. And then we recognize the perfect square trinomial, and once we recognize the perfect square trinomial, use distribution. In just a few minutes, we'll introduce Pascal's triangle more thoroughly, and then you'll be able to see a little bit differently how you can use a plug-in method rather than distribution if you feel more comfortable, because it tends to get pretty long otherwise. So in question number 4, you'll notice that there is an A, B, and C. I'm going to do A as an example, and I expect that you practice using B and C after you get done with the video. Okay? Your first step for finding each of these products is going to be rewriting this cube as a binomial to the 1st degree and a binomial to the 2nd degree. Once you do that, what you have is a perfect square trinomial, so that's where we are going to start our exploration. If I can find my written work. So notice how I've expanded that second binomial squared to be the perfect square trinomial that it is. Now I'm going to distribute all of these terms throughout the trinomial, and this is the resulting expression. Now I'm going to combine like terms to get my final simplified solution, x to the 3rd, 6x squared plus 12x plus 8. You'll notice that there is very little difference between A and B, so your answers are going to be very similar to both of these expressions. The simplified result is going to turn up certain terms negatively as opposed to positively. We'll talk more about that when we introduce Pascal's triangle more thoroughly. You're going to have to be careful about the way that you simplify this one because that coefficient is 2 different numbers, 2 and x. So just be careful and thorough when you simplify that one. All right. D, likewise, I'm going to do with you, and I expect E and F to be worked on after we get done with the video. All right, the first thing we have done is we've rewritten it as a binomial to the first degree and a binomial squared. Now we recognize the binomial squared, what it is, a perfect square trinomial. We expand it out. Remember, it's a minus sign, so this is going to help you with b if you have not begun b yet. Then you're going to notice when you distribute, you're going to get these simplified numbers once you're completed. Then after that, I'm going to go ahead and combine like terms, and the resulting answer is that. You're going to notice that E and C are similar to one another as well, so you should be getting the same numbers there. It's kind of a check method there to help you out, make you have some redundancy, and with that redundancy comes confidence. Okay? So all we're doing here is distributing throughout. Just remember to carry your negative signs where they are appropriate so that you can get the proper sign on your final answer. When this video is concluded, please go back and practice these. It's going to be paramount that you get this practice down just so that you have the repetition necessary to feel confident distributing these numbers together. Moving on, let's officially introduce Pascal's triangle as a triangular array of polynomial coefficients. That's going to help us throughout this unit as we try to simplify these very large polynomials that we're going to be working with. Here's some concepts that you want to continue to learn and remember. This difference of squares is there. Okay? A perfect square trinomial is there. And now we have these these general forms of binomials that are cubed. And that is not the same as the sum and difference of cubes that we introduced in notes earlier this week. These are two different things. As you notice, I had to erase on that video because I actually created this in the notes at first. You may still have the scribble marks if you did it in pen. And you'll notice how very different those two terms actually are. As an additional point of emphasis, I've gone ahead and found a very large version of Pascal's triangle, and I've inserted it into my notes there. On the next page, you'll notice there is a condensed version of it, and I did this just so you can see that it continues on and on and on and on and on. Pascal's triangle is very interesting because you can notice here there's a little pattern on how to find the next coefficients. If we go here, if we go here, you can see where it actually begins to become a pattern. So 1 and 2 become 3. 1 and 2 become 3. So within Pascal's triangle, you'll see a smaller set of triangles as well. And it's at the point of these triangles that you notice how the next sum of the rows is determined. So Pascal's triangle is a very interesting pattern, and it has lots of practical uses. We'll talk about that a little bit in class tomorrow. I'll demonstrate some of the ways that it can be utilized throughout mathematics. Lots of patterns and lots of different applications. All right, as I had said, we're going to take a look at Pascal's triangle, the condensed version here. So you don't have to copy down that other one. So you have one here for you. You'll also know notice how it's lined up, so you'll be able to utilize these shortcuts once you see how I do them in the next several slides. So in our extra practice, what we're going to do here is we're going to practice different operations of polynomials. Most of this is going to be done in class tomorrow. However, there will be a few that I assign at the end of this video as you-dos. And I'm going to go ahead and call question number 2 a you-do. Question number 1, very simply, what we're going to do here is we're going to combine like terms. The reason I'm not going to use the distributive property is because there's a plus sign between the two of them. So I'm just going to combine like terms here, and once I do that, I get this simplified trinomial. This one here is going to be a classroom practice, so you can go ahead and skip 3 for right now. We're going to go down to question number 6, I mean. Questions 4, 5, and 8 and 9 are going to be classroom practice for tomorrow. But specifically, I'm going to complete question number 6, and I'd like you to follow that up with this similar problem, question number 7. See if you can determine the correct way to simplify that. So what I'm going to do here, because this is 3 binomials being multiplied together, there is no factoring shortcut here. There is no perfect square trinomial. So I'm just going to pick 2 of them and multiply them together. I've chosen to multiply this one out for you so you can see clearly how I'm using the distribution method to make this work. So I get x squared minus 2x plus x minus 2 times x plus 6, and then I distribute that one more time. Well, sorry, I combine like terms first. X squared minus x minus 2 times x plus 6. I distribute that again, and I get x to the third plus 6x squared minus x squared minus 6x minus 2x minus 12. Combine like terms, and I get x to the third plus 5x squared minus 8x minus 12. And that's how you would solve that problem, multiplying these 3 binomials together. Pause the video now and practice number 7 on your own, and we'll continue on. All right, the last 2 examples that I'd like to go over right now are questions numbered, the last example I want to go with you is question number 10. Immediately following this, I want you to try question number 11 using Pascal's triangle specifically to expand this out, okay? All right, so what I've done here to begin with, for starters, is I've utilized Pascal's triangle, the 4th row of it, as my template. When you do question number 11, you'll need to go back over and get the 5th row of Pascal's triangle as your template. So A, in my particular example, is the term 4t. So everywhere you see an A in this template, I'm going to replace it with the number 4t. In my template, I have a B, and the B is -2. The symbol matters when I plug it into this particular array of variables. So now that we recognize what our A and B terms are, now you can see how to plug them properly into the template that has been given. Now you'll notice that the negative symbol is responsible for changing all of our plus signs within the template that we are using from Pascal's triangle. You'll notice also that when I raise a base to an even numbered exponent, this negative becomes positive. When I raise a negative base to an odd exponent, this remains negative. As a very important property to remember so that we can properly identify our pluses and minuses as we go throughout this particular shortcut method. Now the reason why it is a shortcut method is because I would have to multiply this out 4 times doing distribution each time, making infinitely long strands of A and B variables, where if I use this shortcut instead, it cuts down on my steps considerably. So notice how we do this so that it simplifies out. Now what you want to do is you want to grab your template, that's row number 5 of Pascal's triangle. You want to plug in your A and B terms, simplify them down, and see if you can come up with the answer. Be ready to discuss all of the you-do problems with your table mates tomorrow, as well as in a class discussion, so that we can clearly identify the places where we need to reteach so that we can move forward with these operations of polynomials.